And by the way, we call this, generally it's called airway smooth muscle. We could distinguish bronchial or tracheal. Okay. The airway smooth muscle is a little bit all encompassing here. Okay, so acetylcholine is going to cause those cells to constrict. Okay. We have a group of cells called mast cells. Who's heard of these before? Yeah. Where? Microbiology? All right. What do mast cells do? Lots of things, but they basically are permanent residents of our tissues. Okay, so most of our tissues have some number of mast cells. And these mast cells are interspersed within our smooth muscle and epithelium. Okay? And they respond to irritants. It could be chemical irritants, it could be biological, okay? It could be a pathogen here. Okay. But histamine, you've all heard of antihistamines, right? Histamine is a signaling molecule. Okay, and antihistamines are ways of preventing that signaling. Okay. So this is, in a way, it's an immune response. Okay, but it doesn't have to be strictly to bacteria. It can be to could be to other pathogens. It could be to just chemical irritation. Right? They can respond to lots of things. Okay, so histamine coming from mast cells will also cause bronchoconstriction. Okay, so during rest and digest, you've got the parasympathetic nervous system keeping the airways smaller. We've got a little bit more resistance, but the benefit is that we keep surface area down, okay? And which allows us to not lose as much water and things like that. And most importantly, it keeps that anatomical dead space low, okay? Then with the mast cells, this is our ability to respond to something irritating in the environment, okay? And if we do that, we can minimize our exposure to it by keeping airways small. Okay, so bronchodilation causes our smooth muscle to relax more. And this stimulus comes from the adrenal medulla. Okay, what comes from the adrenal medulla? Epinephrine. Okay, epinephrine comes through the adrenal medulla. Right. So there is no sympathetic nervous system here directly. Okay, sympathetic nervous system is only going to work here through the adrenal medulla. Okay. But if we're exercising, epinephrine levels are going to come up, or if we're running away from a dinosaur, epinephrine levels are going to come up, right? And what this does is it allows us to, while we're breathing, much more rapidly and more deeply, it allows us to reduce the amount of resistance to airflow. Okay, so we can exchange lots and lots of air. Okay, and yeah, we'll have a little bit more dead space, but we're breathing very, very rapidly, so it's not too much of an issue. We can overcome that inefficiency. Okay. So these are the three different factors. We've got histamine, parasympathetic nervous system releasing acetylcholine, and then we've got epinephrine. With me? Any questions about the circumstances in which you might release these? Yeah.
Well, do we have to know exactly what the histamine does to the smooth muscle?
Yeah, we're going to talk about what histamine does to the smooth muscle. We weren't, but thanks to you. Talk about it. Everybody says thanks about it. Yeah, we're going to talk about that. You're not going to see anything totally new here. So, all right, bear with me. Okay. No groaning. All right, beta 2 receptor. Where have we seen this before? Skeletal muscle arterioles, right? So not skeletal muscles, but skeletal muscle arterioles. Arterioles serving skeletal muscle. And what happened when we stimulate beta 2 receptors in skeletal muscle arterioles? They dilate, okay? Allowing more blood to get to our skeletal muscles during the fight or flight, okay? Or God forbid, exercise. Okay, so what does it do here? Exactly the same. Okay? Nothing different at all. Okay, so epinephrine will come along and it will stimulate the beta 2 receptor. And beta 2, just like beta 1, uses the G stimulatory protein, and we get cyclic AMP, right? And just like before, PKA is going to stimulate the myosin light chain phosphatase. Okay, takes our phosphates off our myosin, and we get less contraction. Okay, so exactly what happens in smooth muscle of arterioles. Here we're talking about airways, okay, but it's exactly the same thing that happens in arterioles. Okay? And we will see beta 2 in other parts of the body, but it's always going to do the same thing. It's going to be found on smooth muscle that dilates. Okay? And it uses the same mechanism. Simple stuff. Okay? No, it's not simple, but once you learn it one time, you see it again, and you get those types of questions. Very easy. Okay? So that's how we relax our smooth muscle. Okay? Questions on that? What's the ligand? Epinephrine. Okay, so it's not norepinephrine. There's no nervous system connection here. Okay, it's only circulating epinephrine as a hormone. Quite flat. Here's the other side of it. We've got the same muscle cells. Okay, so it's not different muscle cells. These are the same airway smooth muscle. They're using the GQ system. Okay, and this one works exactly like what we've seen with which one? Which receptor? What part of the body? Where do we constrict smooth muscle? Yeah, just like with the arterioles, right? Alpha 1, something like that. Okay. So here we have two receptors, or two types of receptors. Remember, there's lots of these on the cell. H1, which is for, take a guess. Histamine, very good. And M3, M for muscarinic. This is the one that's going to respond to acetylcholine. Okay. So these use the GQ, G protein, right? And we're doing the opposite here at the end, right? PKC is going to come along, and whereas PKA was stimulating the myosin light chain phosphatase, here we're going to inhibit it. And then calcium is going to come along and stimulate the kinase, okay, indirectly. So we get more contraction. Okay, now all of you, this is a great example of why we have these different G protein systems, right? What if we had only one G protein system? We couldn't have competing systems in the same cell, right? So we have a GQ system, which helps us constrict, and we've got the GS that helps us dilate. Relax, okay, in the same cell. All right, so remember we said there's some cumulative material, right? This is part of it. Okay, so you're going to have to remember this stuff from before, but it's kind of similar, right? It's kind of the same, slightly different context, but you do have to remember your G protein coupled receptor pathways. Okay, so let's put these things side by side. Okay, and talk about mast cells. Okay, any cute? All right, mast cells. All right, same cell here at the bottom. When we have some kind of stimulation to these mast cells, which comes through chemical irritation or bacteria, whatever, okay, the response of this mast cell is that it's going to release histamine. Okay? And histamine will bind to the H1 receptor, okay? And we get bronchoconstriction. Okay? Those cells will activate their myosins, and those myosins are going to contract. And the airways are going to get smaller, and we get less exposure to irritants, pathogens. And the parasympathetic nervous system works on the same pathway, although different receptor. Okay. This is what's happening most of the time, right? Rest and digest, unless you're constantly stressed. Nope, none of you, right? But most of the time we've got parasympathetic tone. That is, the parasympathetic nervous system is constantly giving signals to keep our airways a little bit on the small side to keep keep that dead space down. Okay. All right, and then flip it around. If we've got a situation where we've got fight or flight, then we've got our epinephrine signaling to the beta 2 receptor. Okay. There's one other component to this that I haven't told you, so here it is. Epinephrine also can act on mast cells. Okay. Why would we want to act on mast cells if we're epinephrine? Yeah, to inhibit them, right? So we don't only want to stimulate bronchoconstriction because there might be a competing signal that would prevent us from dilating as much as we want to. Okay, so we block the release of histamine. Okay, so epinephrine will diminish histamine. Okay, so we've got beta 2 receptors on smooth muscle that relaxes, right? And we've got it on mast cells as well. Okay, ready for a question? All right. So we've got a couple of medications here that it's probably worth knowing in the long term. Although, just for test purposes, I'll tell you that I'll give you the what type of antagonist it is. Okay. But you've heard of a lot of these. Have you ever heard of albuterol? Maybe you don't know what it is. Maybe you do, but you probably heard of Claritin. Yeah. Half this room is probably not good. Caffeine. Nobody's heard of that. It's just, okay. All right. So with which combinations of medications below would there be the strongest bronchoconstriction? Let's say you really wanted to constrict your bronchi. I don't know why, but let's say we want to constrict our bronchi. Which combination here, based on how they work, you have to review things here, is going to give you the most bronchoconstriction? Okay, take some time here and talk it over. You shouldn't like the question. Hang on. Where it says bronchoconstriction there, let's change that.
Oh, okay. It's dilation?
Good idea. Bronchodilation. Yeah. Sorry about that.
I don't know. Do I need to push anything?
All right. Let's see how we're doing here. Do you like it when I let you change your answers?
Yes.
You don't? Why not?
Yes.
It seems like it would be a good idea. Ooh, that's good. Okay. Peer pressure, come on. Really? Okay. Somebody tell me what albuterol is going to do. What would it do?
Dilate.
Dilate. Okay. So it's going to dilate. Why? Because it's stimulating beta 2, right? Sort of taking the place of epinephrine. What kind of person takes albuterol? Yeah, asthma. So the mist that people will inhale is albuterol, or classically it's albuterol. It could be some other version of a beta 2 antagonist. Okay, that's right. So when somebody has asthma, you want to dilate, so bronchodilation. Okay. What about Claritin? H1 antagonist. So what does H1 do when it's stimulated?
Constrict.
Constricts. Okay, so an antagonist would allow dilation, right? So H1 antagonist would promote dilation, just like albuterol. Okay. What about caffeine? So phosphodiesterase inhibitor, which pathway is this going to work on? Is it a pathway that's concerned with constriction or with dilation? The dilation pathway, which, no, is it? Yeah, it is. It's the beta 2 receptor that's going to use cyclic AMP, right? Okay, so Phosphodiesterase will do what to cyclic AMP levels? Phosphodiesterase breaks down cyclic AMP, right? So an inhibitor is what does what? Prevents it, allows it to persist longer in the cell, right? So it's as if we get prolonged beta 2 stimulation, right? How are you thinking about it? Some of you are changing your minds. Let's think through that again. Caffeine is going to prolong the amount of cyclic AMP in the cell. I see a lot of you changing your answers.
I think it's gonna die.
That's okay. You understand? Do you understand it though?
Yeah.
Let's take a look here and refresh our memories, right? So if we're going to, okay, so phosphodiesterase is the enzyme that breaks down cyclic AMP, right? So phosphodiesterase would be working here to break down cyclic AMP. Okay? So if we're inhibiting that, what happens is we get more signal, right? So the epinephrine signal comes through stronger, right? We get more bronchodilation with caffeine. Does that make sense? Okay. So the correct answer here is C. Any questions, concerns? Okay, we got a little bit more to go. Oh, by the way, we can update your chart. Do you guys have a chart? Hit your bed somewhere, you can see it first thing in the morning. Last thing at night. Dream about it. All right. So we've added the blue ones here. H1 and F3. All of these things are going to work through that GQ pathway. Okay. So when in doubt, it's probably GQ, right? Why not? If you have to guess, right? The odds are in your favor. The other thing I can tell you is, of course, the beta receptors. Beta receptors, they always use GS. Okay, that's one way to remember that. There is a beta 3 found on adipocytes. We might talk about that, but it's a GS as well. Okay, update your charts. If you have a chart. If you don't have a chart, get a chart. Make a chart, print that chart. Okay, so now we've talked about all the things that sort of oppose our ability to ventilate, okay, the sources of resistance, okay, and we've also spent a little bit of time here talking about the different reasons and the mechanism for altering airways radius. Okay, some of that has to do with resistance, but concern ourselves with anatomical dead space and irritants and so forth. Okay, so last part is alveolar ventilation. This is the easy part. Okay, so we've got a term here which is called minute ventilation. Okay, and minute ventilation takes two variables into account. One is the tidal volume. So as you're sitting here, relaxed, on the verge of sleeping or beyond, you've got a relaxed breathing in and out, inspiration and expiration. And it's about 500 milliliters. Okay, the amount of air that you bring in, or conversely, the amount of air that you breathe out, it's about half a liter. Okay? So like the tide comes in and out, your breath comes in and out. You've got 500 milliliters of it, usually. The rate is how many of these breaths you take in a minute. Okay, at rest, 12 is a good number. Okay? And in a way, this is kind of like cardiac output, right? We want to know how much volume is moving per unit time. Okay? Instead of contractions per minute, beats per minute, we have breaths per minute. Okay? And instead of a stroke volume, we have a tidal volume. Okay, so they're kind of similar values. Okay, so conceptually, we could say that a tidal volume, a minute ventilation is the volume of air moved per minute. Okay. So we don't count the air twice, by the way. Tidal volume is either in or out and above. Simple, right? Yes. Okay. So let's bring it back to this idea of anatomical dead space. In this diagram, we have the anatomical dead space represented by this little segment here at the top. Okay, and it's about 150 milliliters at best. And then all of the alveolar gas that you see here labeled as alveolar gas, this is what's in your respiratory zone. Okay, so you've got conduction zone at the top, that's your anatomical dead space, just moving air through, there's no gas exchange taking place. But then you've got all this volume at the bottom, which is your alveolar gas. Okay, and this is the respiratory zone where we do have gas exchange taking place. Okay, so what this illustrated is trying to show you is that when you exhale, okay, on the left, you're in the rested state, right, between that exhalation and the next inhalation. You've got some air in your conduction zone, about 150 milliliters, right? That's all the air from your nasal passages down to your bronchioles, okay? And then you still have a bunch of air in your alveoli, okay? And when you breathe in, we might breathe in a tidal volume of 500 milliliters, okay? And what happens is that some of that air that was already there, 150 milliliters, gets pushed down. Now it participates in gas exchange, okay? And that new fresh air, that breath that you've taken in, 500 milliliters, only a portion of that makes it to your alveoli, right? A big portion, but only a portion, not all. Okay, so there's 150 that's left over. Okay. So when you take that breath in, not all of the air gets to your alveoli. Some of it's just, we got to move that air in order to get the rest of it down to your alveoli. Okay. So proportionally, we've got 150 milliliters out of 500 that is not participating in gas exchange. Okay. So this is why we want to be able to make sure that this is minimized, right? If we're spending energy to inflate our lungs and move 500 milliliters of air, we want as much of that air, as much of that 500 milliliters to make it to our alveoli as possible. Okay? So if we dilated, what would happen to your dead space? Increase, right? And then maybe it's 200 milliliters out of 500. Okay? So during a state of resting and digesting, we want to keep our dead space relatively small. Okay. So we have this other term. We said the minimum ventilation is the volume of air moved per minute. But if we want to know how much air is moved to our alveoli, that's a different question, right? So minute ventilation is air moving in and out. But if we want to know how much air is being brought in to participate in gas exchange, we need to take away the dead space, right? All right, so that's what this equation is here. Tidal volume. Take away the dead space, right? And then multiply by the respiratory rate. Okay, so we could say that this is the volume of air moved to the alveoli, or to and from the alveoli per minute. Okay. And this is what matters, right? If we want to concern ourselves with getting gas to our alveoli, we want to know what this is. Okay, one final question. Oh man, it's so tiny. Like tiny questions or big questions? Big questions and little answers here. Okay, can you read it? You can. All right, let's talk about antihistamines again, just because they're fun. All right, H1 antagonists. Again, you'll never live these down for the rest of your life. You don't have to deal with this stuff. Okay. Claritins or these are very common over-the-counter medications. Okay. How would these medications affect the respiratory system? You like these up-down questions?
No.
No? Me too. Very good, great. You're going to have fewer of them on the next exam. How do you feel about that? Okay, good.
Object.
They were out for a lot of you. There were opportunities for partial credit. So, all right. So we're asking about surface area of the airways, resistance, and alveolar ventilation, right?
Okay. So,
You're taking an antihistamine. What happens?
tidal volume. So more, if you get an.
Surface area, resistance, alveolar ventilation rate is the easiest to figure out.
Resistance.
You want to take one of them, somebody? Who wants to tell me about resistance? Nobody. Yeah. All right, by increasing the radius of our airways, resistance will decrease. Okay. H1 antagonists, does everybody agree? H1 antagonists should cause dilation?
Mm-hmm.
Yeah. Okay. Dilation occurs and resistance goes down. Right. What else do we have? Surface area. That's an easy-ish one. What's going to happen to surface area when we dilate our airways? Increase, right? Instead of small airways, we've got big airways, which means there's more surface area. Okay. Alveolar ventilation rate. This one is a little bit complicated depending on how much you want to think about it. So let's keep it simple. What are we going to change about alveolar ventilation rate? Are we changing the tidal volume? Are we changing the anatomical dead space? Or are we changing breaths per minute? Dead space. Okay. Now, so what's going to happen to dead space? It goes up. All right. So the alveolar ventilation rate should do what? Go down. Right. With more dead space, we have less air going to our alveoli per minute. Okay. Now, we can expect that our lungs, our bodies may not like this, right? So there would be some compensatory changes, some physiological adaptations that we can talk about. But just strictly in terms of the immediate result of this antagonist, those are the things we're going to have, right? It's going to be an increased decrease. What do we have? Okay, we're going to have more surface area. We're going to have less resistance, and we're going to have less alveolar ventilation. Yeah, it's going to be easier to breathe, and maybe we'll end up with a bigger tidal volume. You can imagine some things might change, right?